Okay, we'll be starting in about a minute. John, I'll be turning things for your introduction in a minute.
He's unmuted right now.
And I believe, John, you are unmuted.
Ready?
Okay, it's 1 o'clock Central Standard Time. Hello and welcome. You are attending the AASHTO Pavement ME Design webinar on FWD deflection data analysis and Backcalculation tool. My name is John Donahue. I'm a construction materials liaison engineer with the Missouri DOT. I'm also the current chair of the AASHTO Pavement ME Design Product Task Force. And I'd just like to make a couple comments before I turn it over to the instructors at Applied Research Associates and say that this is probably the one product I was looking forward to for a number of years, simply because there's been difficulty in finding a back calculation tool that was accessible to everyone. Usually there's several out there, but not everyone had access to them. They were not always really kept up to date as far as being able to read all FWD files, and they didn't necessarily have all of the tools that this particular product has. This was released last month, early July, as part of the Pavement ME Design 2.4 version. So it is now out there and available for AASHTO licensees. And with that, I will turn this over to Harold Von Quintus.
Thank you, John. And with that, we'll go ahead and start the webinar. To begin with, I think Chad Becker sent a message out earlier. All phones from the participants are being muted or are muted. We'll ask the questions through the chat box. And we'll hold the questions till the end after the demonstration, and then we'll answer all the questions that are sent in, or as many as we have time to answer. And if we do not get to all of the questions, then we'll send out a memo to all the participants noting what the question was and then the answer to the question itself. So all questions will be answered. If they don't get answered today, they'll be answered later this week via a written information. So as we did in previous webinars, we wanted to briefly note some of the process for enhancing the software. The suggested revisions to the software, either as improvements or enhancements, are received from users and AASHTO members. The Pavement ME Design Task Force monitors all the suggested improvements or requests from the community. They also monitor various projects that are ongoing through NCHRP, FHWA, and other pool fund studies that would improve the capability of the Pavement ME Design software. The task force reviews and prioritizes all of these suggested improvements and then identify on an annual basis those that they want the software to be enhanced to. Very briefly, this is the Pavement ME Task Force membership, about 10 different members. If any of the participants see something that they want added as an enhancement down the road, they can either send it to the task force member, to the website, AASHTO Pavement ME website, or to our help desk. And that way the task force members will get all the suggestions in the future. So with that, we're going to start with our first poll questions. And Chad, you're going to have to, yeah. We have two poll questions we'll ask initially, and we'll bring these up. So if you would, these are our first two poll questions. We'll give about a minute for each. So if you could answer the two questions, that would be great.
Presentation.
So we have about 30 seconds left. So I can pop it up now.
Yeah, it should keep going.
Okay. Okay, so you can see it? Okay. Okay, we have about another 10 seconds remaining. Okay. With that, we close the poll. You got? Okay. I'm going to cancel it now, and we will apply, right? Okay. So I'm going to close this. Okay. Okay. So our presentation or the webinar this afternoon is broken into 3 different segments. The first is we'll go through a presentation of the back calculation tool, which will be an overview. The second part will be a demonstration of the back calculation tool, and then the third part will be our question and answer period through the chat room, the questions that we receive during the presentation. Again, as we're going through the presentation and or the demonstration, anytime you have a question, please add it in the chat room, and then we'll answer all the questions at the end. So begin, first of all, with some background information. As John said, not only John, but many members of the task force wanted a comprehensive tool to assist in the analysis of the deflection data for rehabilitation design, and also to assist in the back calculation of elastic layer moduli that could be used directly into the pavement ME rehabilitation design strategy. And so that was the objective, that was the purpose of this enhancement. The back calculation tool or program is executed, it is independent of the pavement ME design software, but the results or the outcome of the back calculation process is formatted according to the pavement ME design input requirements. And as part of the demonstration for the second part of the webinar, we'll go through that process in terms of setting up an actual input file for the pavement ME from the back calculation process. I would note that there are 2 versions of the program. One is the English-based units, and then the other is the SI-based units. So both English and SI-based back calculation tools are available. The back calculation software package or I should say numerous back calculation software packages were requested by the AASHTO task force. One of the requirements for using different back calculation programs, however, was AASHTO wanted a copy of the source code to ensure that it could be maintained, updated, along with pavement ME over the time. The only program or software that was provided was EverCalc in terms of the source code being provided to the AASHTO Payment ME Task Force group. And that was, I would like to issue a special thanks to Jeff Olmeyer with Washington, also Siva with FHWA, and then Linda with Nichols Consulting. Engineers provided, the background information, the user manual, and obviously the software itself for incorporating into the back calculation tool generated for AASHTO. So a special thank you to Jeff, Siva, and Linda for their current efforts and previous efforts in this item. There's also other documents and information that was used in setting up the back calculation tool, and I'd just like to recognize or note those at this time. One was an FHWA long-term payment performance project on back calculation. It was called the Back Calculation of LTVP Deflection Data Report. Jane Yang was the FHWA contact. And one of the key outcomes of this, from this study, was an automated back calculation process using the long-term or specific for the long-term payment performance program. Information from that study provided a lot of the criteria, tools, and other analysis from a deflection analysis standpoint that was incorporated into AASHTOware's back calculation tool. Before that, Cheryl Richter was the FHWA contact for one of the first back calculation studies through the long-term payment performance program, and this was conducted in or reported in 2001. Information from that study was also used. One of the more recent, also a long-term payment performance study, which provided information in setting up the back calculation tool, was a study where Larry Weiser was the FHWA contact. It was a characterization of existing HMA layer for ME payment rehabilitation design. And then also the MEPDG user manual, the hard copy. And then there were also multiple projects that were sponsored by various agencies as well as FHWA that have been completed over time, that information that was included and reviewed for the back calculation tool. So from that background information, we'll move on to the products that are available. There's basically two products for doing payment ME input level 1 rehabilitation design. Obviously, one of the projects is the back calculation tool itself, or the software package, which again is separate from the payment ME design software. It's a separate package, but it's available on the payment ME website. The other product are two documents. One is the user manual and or the help manual, which complements the original MEPDG manual of practice related to back calculation, but this user manual is specifically focused on the use of EverCalc that's available. The task force also suggested that various chapters on back calculation be extracted from the EverSeries manual related to EverCalc. And those are also available on the website for users to see and review in terms of back calculation. So basically two products, documentation of the user manual and extracted chapters from the EverSeries manual, and then the software package itself termed the back calculation tool. So overview now, some of the features of the tool itself we'll go over. The back calculation program, again, is run independently. So it's not directly a part of the pavement ME rehabilitation design package, but the outcome or results from the back calculation tool are formatted in accordance with the pavement ME, so we can use those and automatically setting up a pavement ME design run, and we'll demonstrate that later. There are 3 parts of the back calculation tool. The first part is the pre-processing tool, getting ready for back calculation, and we'll go through each of these separately. The second part is the back calculation, or actually doing the back calculation with EverCalc and determining the elastic layer moduli. And then part 3 is the post-processing part, where the user can look and review the results from the back calculation process, and then in setting up a run or a file for actually running the pavement ME design software. So now starting with an overview and features of the tool itself. This is the primary screen that you'll see when the back calculation tool is opened. It's set up very similar to the pavement ME in terms of format or screen structure. The parts on the upper left-hand side you can see is a series of steps that the user will go through and doing or executing the back calculation tool. There's a series of about 9 steps that the program does. The first is inputting the FWD data. The second, identifying the segmentation sensors, or the sensors that are going to be used for the segmentation of the project. And then steps 3, 4, and 5 are really coming up with the segmentation or the design segmentation itself, and we'll review those a little bit later. 6 is identifying the structure for the back calculation through EverCalc. Step 7 is the actual back calculation program. Step 8 is looking at various or 2 specific physical features of the pavement structure that have an impact on the back calculation results and how they're going to be used, which are also inputs to the pavement ME design program. And then 9 is simply the step exporting the results from the back calculation tool to pavement ME design. Another item for the back calculation tools on the lower left-hand side of the screen, and this is called the guided process. It provides similar to pavement ME in terms of identifying, defining, and providing input for each step and process through the back calculation process, and even some of the terms. And basically, this guided process provides the user or guides the user through the process, which also provides a description of what the feature is and on the screen, and what is its function and how that is used in terms of the back calculation process itself. The other thing is that on the as we're going through the back calculation screens, the back calculation tool help manual is identified here in terms of the manual, so a user can click on the manual, this button, and the manual will pop up automatically. We'll demonstrate that also when we get to the demonstration, but this is included to provide immediate access to the user on different parts of the back calculation tool itself. Okay, so we'll start with now part 1, the pre-processing deflection data. The pre-processing deflection data has 4 subsets. We're going to import the raw deflection file from the field testing that's collected with the FWD. The second part is we're going to then clean up that data file and or filter that data file for use. We'll then do the segmentation of the overall project. And then from each of the segments, we'll identify pavement structure. In other words, what's our simulated pavement structure for each of the segments or the design analysis segments. And then from those 4 steps, the back calculation tool automatically generates the input files for EverCalc for each section. So starting with the first importing FWD data file, what you'll see is an FWD data file. And since many data files exist historically and currently exist that different agencies use, there are a series of converter files that take the more common deflection data file generated by the users and converts those into a file that's required by EverCalc for the back calculation process. So these are standard converter files that are used depending upon what the base file that the users collected the FWD deflection data in. And these are shown on the file here. So we're going to then read the data. This just shows it's a Dynatest version 20 FWD. So we'll download that file, and once we download and parse that file, you're going to, after we read the FWD file, then the data is going to be organized from the original data through 3 separate tables that have been set up. So the first table, basically as shown here, that's in the upper table. Basically, it contains a list of stations and attributes that would include temperatures, air temperature, surface temperature, pavement temperature, elevations, longitude, latitude, whatever available from the deflection data, and organizes it into this deflection data file. The second middle table, or the second set, middle table, shows the sensor configuration, and that's where the sensors are located on an XY grid basis. Most of the times they're all going to be on an a sensor spacing along the X-axis. However, some agencies and users offset some of the sensors based on a lateral displacement from the loading plate. And so we have an XY grid for identifying where the sensors are located. So then the lower table, table 3, shows the deflection data for the drops from each station selected in the upper table. So example for test point 3 as shown on the screen here, this shows, table 3 shows all the deflection table or the deflection data and drop load data measured at test point 3. Moving the cursor to a different test point, then the deflection table in the lower table would change. So the lower table, table 3, is directly tied to table 1 in terms of each of the test points. So that's importing the FWD data file into a data format that's accessible and used by EverCalc. So the second part of the pre-processing the deflection data is the data cleanup and filtering. When we say data cleanup, none of the actual data that's in the raw deflection file is ever eliminated. It's always there. It's never deleted. But we want to identify or highlight deflection basins, test points that may be outside what you would normally see with elastic layer theory and other problem issues with deflection data, and that's the purpose of deflection data cleanup and or filtering. So the program, the Backcalculation tool, classifies the deflection basin into standard 4 types that were developed by FHWA many years ago. These 4 deflection, and you can see that in the lower right-hand corner, called the basin classification, and these are all shown as typical for this one set of deflection data. But the program classifies deflection data into basically 4 types. Those are defined as typical. That's standard in accordance with elastic layer theory. Type 2 is where we have a significant decrease in deflection data between 2 adjacent sensors, or where we may have a reverse curvature in our deflection basin. Type 1 is defined as deflections where some of the sensors are greater than the deflection under the loading plate. And then type 3 is where we have non-decreasing deflections at adjacent sensors. And these 4 types are illustrated in this visual aid. And you can see typical on the upper left-hand, very consistent with elastic layer theory. Type 2 is still consistent with elastic layer theory, but it has kind of a reversed curvature in some of the deflection basins. Type 1 is where we have deflections from the outer sensors that are greater than the D0, or the deflection under the loading plate. And then type 3 is where we have non-decreasing deflections throughout the deflection basins. In other words, we either have between a couple of adjacent centers either equal deflections at the sensors, or the sensor furthest from the adjacent center, furthest from the loading plate, has a higher deflection than the sensor closest to the loading plate. And since type 1 and 3 are not used or within the back-calculation process, because they're not inconsistent with elastic layer theory. Okay, the pre-processing, still pre-processing deflection data. This just shows the initial, the segmentation sensors that are used. There's 3 sensors, or 3 sensors that can be used, or no more than 3, I should say, can be used. This just defines for the first one, D0, or the sensor one of the sensors can be any of the sensors. The second one can also be any sensors, as well as the third one. The key is that the segmentation is based on whatever the user defines as the 3 sensors, and they can be any of the sensors included in the deflection basin itself. So there's also filters for once these 3 sensors are selected, and the user doesn't really have to select. The user can select 1 sensor for segmentation, can select 2 and or 3. Doesn't have to be 3. But then there's a series of filter charts that the user will use. One will be through the drop load. The other will be the test type, and the test type could be in different directions. Maybe outside, inside lane, could be measurements at cracks, measurements, mid-slab measurements. So however the test type is identified by the user itself. The third, and probably the more important, is the basin characterization. And then a fourth is the lane and or direction itself. There's 4 standard filter charts that are developed, and then the user can select what he or she wants to use in terms of filtering the data for the segmentation process. What's called the preliminary segmentation is done by the software. This screen just shows the results from the preliminary segmentation process. The preliminary it's an automatic process based on the cumulative area method. That's the same process used in the modulus back calculation software itself. And modulus back calculation software package is the one developed by the Texas Transportation Institute for the Texas DOT. But the automated process is based on the cumulative area method, and that's used also in the AASHTOWare back calculation tool. And that's just shown here. And you can see that for sensor 1, there's 4 segments per sensor. The sensor 18 inches from the loading plate, there's 5. And then the sensor 60 inches from the loading plate, there's also 5. They do not necessarily coincide with each other, depending upon the sensors that are used. The other segmentation is the statistical comparison for the segments itself. And this is called the statistical comparison. And basically, it uses the F-test, which is the test for variance, and the t-test, the test for means, for defining if adjoining tests, sets of deflection data, if they're statistically significantly different. And that's shown here. This is also done automatically by the software. And you can see with the statistical, there was also difference. The other, what's called the final segmentation, screen shows the statistical comparison, and then the user is able to, for whatever reason, in accordance with either the preliminary or the statistical, or there could be some physical features along the roadway where the user will want different segments to be identified independent of the deflection data itself. And the user can come and actually put the cursor on a station and note that as the ending station of one segment and the beginning station of another segment. And where the final manual segmentations are identified, they're shown on the manual segmentation table itself. And that's shown here in terms of the final segmentations that are selected by the user. The final ones selected by the user are the ones that go forward from the segmentation process itself. Okay, so now the structure, once the segments are identified, the last step of part 1 is now identifying the structure definition or the simulation for each one. And that's simply the structure definition is shown where all the deflections within the project file are shown, and then each segment is originally clear, as shown on the right here, but then as the user defines the structure for each segment, once it's defined, then it's turned green. And then the one that the user is working on is in a different color. And those that have yet to be initiated are then in, do not have a color. And so that's the way so that the user can keep track of which segment he or she is working in when you have many segments within a project. In many cases, users will simply have one segment, and so there'll only be one. As part of this screen, though, in terms of the EverCalc inputs, because this screen basically sets up the EverCalc inputs, there's a layer number, as shown here, with the number of layers for simulating the pavement structure, the layer number. Then we have layer type. The layer type is simply a generic name for each of the typical pavement layers for both rigid and flexible pavements. And as shown, asphalt concrete, Portland cement concrete, intact, fractured, and then base, subgrade, lime treated, semi-treated. And once these are selected, then that basically defines the Poisson's ratio that's typical, a minimum elastic modulus for that layer, a maximum elastic layer modulus for that material and or layer, and then the seed or starting elastic modulus for that layer. Also, if the user wants to fix a layer, that capability is also in accordance with EverCalc, where the user can identify a layer that's fixed. The other item, thickness. Thickness is not obviously populated. The user has to enter each of the layer thicknesses for the design segment. But all these other features in the table, they're all populated based on what type of material, layer type description was identified by the user in the drop-down area. Okay, now moving on to the back calculation process itself. This is an automated process where the files going back from the pre-processing structure definition are then automatically entered into the EverCalc. Then that is the back calculation process, and then once the back calculation is done, the output is then output for visual observation and use by the user. Again, the separate output is created for each individual segment. The results are back calculated layer moduli, as well as the root mean squared error, which are displayed on charts on the interface. Key thing here is there's no user activity. The process is completely automated, very similar to the FHWA back calculation process for LTPP. So this just shows the outcome of the back calculation process that can be used by the reviewer, or at least the screens. These are the sensors that were used in the back calculation. The user identifies which sensors he or she wants to use in the back calculation. We then have the elastic modulus for a specific segment that appears throughout the project length or the segment length. It can be by layer, and the user can click on and just look at the AC, the subgrade, or look at them all together. Then also very important for each of these test sites, or test points, the root mean squared error is shown. So the user knows with each of these elastic layer moduli what's the root mean squared associated with those values in terms of deciding whether to accept these or to go forward. Another unique characteristic of the back calculation tool is the compensating layer effects, which we'll show that in just a minute, but these appear as graphs in the software. In terms of the root mean squared error, there is some guidance given both in the user manual as well as through the LTPP program. And typically, what's generally accepted as acceptable or good is where we have acceptable is defined as less than or equal to a root mean squared of 3%, and the modulus is within our typical values for asphalt concrete for each different types of layer: Portland cement concrete, granular base, fine grain soils, coarse grain soils. And this just shows the other is what would be considered unacceptable typically, and that would be where we would have a root mean squared error greater than 5%, and or the modulus is totally outside our area of reasonable values. For example, there are some sites in the LTPP where the subgrade modulus or the modulus of an unbound embankment layer is like 200,000 psi, and that would be totally, means the material is not behaving as an unbound material, it's behaving as a bound material. And so this is simply a guide for are our results within what we would consider typical values or within a wide range of values, but they're still possible for the type of material we're reviewing or back calculating. So this is simply a guide for users to consider in terms of whether they want to accept the results or whether they want to change the structure and redo the back calculation. As I mentioned a while ago, the compensating layer effects. There are screens that the user can review to see if we have a compensating layer effects in our back calculation process. Compensating layer effects and or where we may have a layer that is insensitive to the deflection basin because it's a thin layer, and the results generally are dependent upon the results of the adjoining layer, as shown by this screen. We do have the user makes the decision on whether the structure needs to be changed because of these layer compensating effects, or whether the user is just going to accept them and goes forward. What's shown here is there for the data that we see, and this would show the lower layer modulus or the upper layer modulus as a function of the lower layer modulus. And compensating layer effects means that one is inversely proportional to the other. And that's shown here by the slope is negative. So it's inversely proportional. And the R squared of this set of data, and 0.73 would indicate that's a pretty good relationship. And that's what we do not want to see, especially inversely proportional relationship for back calculations. So this would say we have compensating layer effects, and that would indicate we really need to do something. A specific R squared is left up to the judgment of the user itself. This graph can also be used, which is not shown here, but are many of our deflection basins and our test points, are we hitting the modulus upper or lower limit set as inputs to the EverCalc program? If we're hitting an upper or lower bound for the modulus, that also means we may need to change the limits for the layer and or maybe redo the simulated pavement structure. And we'll go through some of these when we do the demonstration. One of the last parts of the back calculation is the physical features of the program. And there's two for both flexible and rigid. One is termed load transfer efficiency, and the other is the void analysis. So the load transfer efficiency for both asphalt concrete and Portland cement, and how we define or how the program defines and calculates load transfer efficiency is defined by the long-term pavement performance program. The void analysis is also defined by the 1993 AASHTO design guide on what the void analysis means, as well as the criteria that was used to establish whether we have voids or loss of support. So there's two sensors used for load transfer efficiency in accordance with LTPP. Those are defined through this box. What's different from LTPP is the user can define different sensors for load transfer efficiency relative to the deflection under the loading plate. And that's kind of shown here. The load transfer efficiency for both asphalt concrete, as shown in our picture to the right, or by Portland cement concrete for transverse joint, they're calculated and defined by through LTPP, as shown here. The void analysis is simply taking the deflections measured for 3 different drop heights or load levels, and defining the intercept from a linear extrapolation back to load 0, and whether that's greater than or less than 2 mils, and whether we have a potential for voids or loss of support or some other unique feature or parameter related to both asphalt concrete as well as Portland cement concrete pavements. So after the back calculation's done, the user accepts the results. Then we go into part 3, or the post-processing part. And basically, this is just taking the input files going through the post-processing and simulation of results, and then outputting that to a payment ME design file for rehabilitation. So the program summarizes the individual drops for each segment. Basically, it uses the average values in terms of modulus and like load transfer efficiency for each segment, uses the averages, and then includes those as inputs to payment ME. It also it has a post-processor which generates an output DG-PX file for use for rehabilitation, input level 1. And that's shown in this screen. So for each segment, for this example, there's 4 segments that were used, so the user could go through each one and define the structure, simulated structure that was used through the back calculation, which is the layer name here. Then shows the average modulus, the standard deviation of that modulus value for each layer, the coefficient of variation, the thicknesses for the simulation, and the Poisson ratio that was used for EverCalc, which are all fed in then to the payment ME design. The other thing it uses, it also then the user will, for each layer used in the back calculation, these were fairly generic values, or what I would consider more a gross characterization of the layers for back calculation. The user will then need to tie these back to the layer description for payment ME and setting up the default values for other inputs for payment ME. So it's used for asphalt concrete, what type of base for payment ME. This was an A1A down to the subgrade, fine grain for the back calculation, but now we're defining it as an A4. So this now ties the layers that were used for back calculation directly to the standard layer definitions used in pavement ME. Okay, that concludes the overview and features of the back calculation tool. We're now going to go through the release information, where the program or the back calculation tool is located, and then we'll get into the demonstration. Okay, so as John said, the program was recently released last month along with pavement ME design software. The user manual is also available, and the authorization code for using the back calculation tool is tied to the license or to your license for pavement ME design. The software and documents can be downloaded from the website. Under downloads for the software, then that gets you to the download, and I'm sure many of you have already went through this, but this gets you to the back calculation tool. It's available itself, which became available on July 10th, and so that's where you do the back calculation tool itself for the program. There are also software installation and licensing on how you download the software separate that will also show. There's the back calculation tool user manual. This is under the documents. And so with the back calculation tool related documents, this gives you the release notes, which are now available, and how you download the software, which is available on the website. We have the user manual that's also available, and then the other document that I mentioned previously, which is also available, and that's specific chapters from the Ever Series user guide that was published by the Washington DOT back, I think, in 2005. Okay, that concludes the second part for the release notes, parts 1 and 2, and now we'll get into the poll question 3.
Get that set up here.
Okay, and we'll bring in the,
Open up 2.
yes. Okay, so this is our poll question number 3. So we'll give about a minute. So if you would, please complete poll question 3. Okay. We see that some individuals are using the chat room. I would encourage as many of you can to ask questions in the chat room. And after we go through the next part, the demo will then turn to the chat room and start answering the questions. But we'll go through a demo of the software after this poll question. Okay. Again, we're going to, we have about 10 seconds left or so. We'll give about another 10 seconds or so, and then we'll close the poll. Okay. I think we've had over a minute, so we'll go ahead and close the poll. So you'll still have about another 15 or 10 seconds, and then the poll will close. Okay. So I'm going to apply. Yeah, let me save it here. Okay, we're going to save the poll questions first. Okay. Got them? Yep. Okay, and then I'm going to close this. Okay, now we're back to, we'll start the demonstration. So we're going to go through an actual demonstration of the program itself, and I'm going to bring up the program just like I would do under an actual simulation. So we'll make sure our license is valid, the program opened, and so I will now go through using an actual demonstration. The demonstration we're going to use, and some of you online may have already seen part of the demonstration because we're going to use the I-84 example that we have from Idaho. This was a rehabilitation design project that the Idaho DOT conducted last year. And the reason for doing that, the Idaho DOT measured load transfer on a flexible pavement. That's kind of a unique feature that many with industry have not measured the load transfer of transverse cracks in flexible pavements. And so I wanted to show that and kind of discuss its use and what that might mean in terms of the pavement ME rehabilitation design. We would hope and encourage future users that use the pavement ME rehabilitation design that both for flexible as well as rehabilitation design for rigid pavements, that the load transfer of those transverse cracks be measured on flexible pavements as well as the joints for rigid pavements, because it has a big impact on the amount of cracking that occurs over time from a reflection cracking standpoint. So given that, our first part is we want to import our deflection data. So first of all, we have to select a type of file. This was a Dynatest version 20.fwd that was used by the Idaho DOT. So I'm going to browse now and find that file. And this lists now the files that I've set up that are .fwd version 20. And so I'm going to select the I-84 file from the raw deflection file that was provided by Idaho. I'm going to open that, and now this loads up and shows our deflection, each test point, where it is in terms of kilometers. You might ask a question now. We're using the English units here, or the English version of the software, but now we have kilometers being in distance, and that's perfectly fine for the distance measuring, but everything else is going to be in the English version. So distance can be both in milepost, it can be in feet, it can be in kilometers, it can be in almost any length measure reference. Okay, so the other thing I want to show, this shows now the plate radius of the plate. You can see with the Idaho, we had air temperature, surface temperature, and pavement temperatures. We didn't have a lane designation, nor did we have elevation, longitude, and latitude, and that's perfectly fine. We would hope down the road that as agencies start using this, that we start in terms of our deflection file, that we start identifying lanes, different types of types that can be used within the back calculation tool itself for more to be used in more information. Okay, so to note the sensor spacing, this shows what Idaho used. No offset in terms of y-axis for the sensors, but we have x-axis. We do have our behind the plate load for the load transfer efficiency that was used, and then the other sensors spaced out at 0, 12, 18, 24, 36, and 60. So there's 7. So I'm going to click on now any test point, and now we see that the deflections at that test point 1 appear in our table 3. The one thing that we have to do here is we have to enter the target load for each of the drop heights. And so I'll do that as I'm going through this. Once we do this entry one time for just one test point, it's applied to all other test points automatically. And so you have to do this once. After it's done once for one test load or test point, then it's done. So that's test point 1. I can go to test point 6, and now all the values are entered. And I can see for both the 9,000-pound drop target drop load, the 12,000 and 16,000 pound. Okay, so I'm basically done with this. So I'm going to hit now save and proceed. And now I'm going to go into the sensor segmentation, and I can select whichever sensor I want to use. I typically use, obviously, the sensor under the loading plate, D0, as one. The other one I typically use is the sensor furthest from the test loading plate. In this case, it's 60 inches or D60. For sensor, the mid sensor, that can be any sensor. We can use 12, we can use 24, even 36, and use that in our segmentation. What I typically like doing is using the sensor the further away from the loading plate that basically equals my pavement structure thickness. And for this structure we're using here, it's about, I think, 19 inches. And so I'm selecting 18 inches for my segmentation. But this is totally allowed to the user. So I selected now my 3 sensors, and I'm going to do the drop height. I can use all sensors to look at for all the how the deflection base is for each 3 of these. What typically like doing is using only initially looking at the data, only using one drop height from or each drop point from each drop load. For example, the 9,000 target, the 12,000, and the 16,000 initially, and just look and see how these vary between the drop heights or different loads as well and how they vary along the pavement. And then also look at test type. We didn't have any in here. The basin characterization, we can have typical and type 2. If you do have type 3, it will show up so you can see where they occur, even type 1. So they all show. Here we only have typical and type 2. I can say I'm going to turn off type 2, and you can see, or turn off typical, and you see we have very few type 2. And that's really good. That says most of our deflection basins, turning that off, are really in accordance with elastic layer theory. And so that may mean the back calculation process will be a lot easier. And of course, we didn't divide this by different lane type, inside, outside, or direction. So now if I go, now I'm going to go through save and proceed, going to the preliminary segmentation process, and you can see we had an error. And this is the one item that when we go to the segmentation, we only want to use one, for the segmentation, one of the drop heights. So what I typically do is just use the kind of the center part, and so I'm going to use the 12,000-pound target load for the drop height for defining the segmentation process. And this is only to define the segmentation. It's going to use all the other deflection data for the back calculation process. Right. Okay, so I'm going to use that one, make sure one part. So I'm going to go and proceed. Now this shows the preliminary, and this is done automatically. We're not going to change anything on this screen, and so we're going to go forward. I would say, we'll say that one of the recommendations that will be made into the future, or has been made, is that the preliminary, statistical, and the final segment are all going to be seen on one screen. And so you'll immediately go from preliminary to final, but you'll see what constitutes the preliminary segmentation based on the area method, what constitutes the statistical segmentation, and then the user can decide, what do I want to use as my final segments for the back calculation process. So, but we'll go through each of these. You can see here we have about 5 different segments. Some of them are pretty close to one another. The other ones, they're significantly different between the preliminary or between these the sensor D0, sensor at 18, and sensor at 60. Now we can show the statistical comparison, and all we're doing is comparing select sensors as we move down the road. Where do we see a significant difference based on the F-test, T-test, on where deflections start to statistically deviate in terms of D0, sensor 18 inches from the loading plate, and sensor 60 from the loading plate. And so this just shows us the general indication, and now we're going to go to the final segmentation. And the user then will decide, where do I want to select my segments for the back calculation process. And so there may be, we could do these by the deflections themselves in terms of the preliminary and statistical. There could be site features that we'll want to consider for the final segmentation. So the user can select as many segments as he or she chooses. We could also do a test point. Each test point could be a separate segment if the user so desires to do that. For this example, though, I'm only going to select 2. I could select, well, let me demonstrate these for resetting the segmentation process. I could select a segment here, and I could go and select a segment here. So that would be 1, 2, and 3 segments, which appears on the table on the right. And these were then the segments. If I wanted to use these, I could select save and proceed, and these would be the segments that would be identified for the back calculation. And so there would be 3 back calculation files set up. I'm only going to select 2. I'm going to put my cursor here, and I'm going to use the segment, the first part, and then I'm going to have another segment that includes everything else. So I'm going to have 2 segments for the demonstration. So I'm going to save and proceed, and going forward to the structure definition. So this is what originally shows our deflection data as we go forward. And now to identify the pavement structure for each of the segments, I'm going to put my cursor and I'm going to click 1. So this now has kind of an orange color, and this is the segment basis I'm using to go forward. And I'm going for this demonstration, make sure I don't run out of time, is I'm going to do what the Idaho DOT originally did for their pavement and doing the back calculation. And so this will be for segment 1. They used, I think it was 5 layers. Okay, and so we have the segment 1 from cores. So we want to find that. It's an asphalt concrete, and it was 10 inches. Layer 2 was a gravel base, so it's got a granular coarse-grained base. That was 9 inches. Layer 3 was an embankment material that was more of a coarse-grained, but on the finer side, coarse-grained material, so I'm going to say subgrade. That was 18 inches. And then they had a coarse-grained subgrade identified was 24, and more of a fine-grained subgrade toward the end. Okay, so you can see that everything's been populated. For this demo, I'm just going to leave everything as what was populated by the program itself automatically to show what the results were, and then we'll come back. So I'm going to then since this one is done, I'm going to hit the apply. So we're going to apply those thickness to that segment. So now I'm going to move on to segment 2. This shows the progress. If we had multiple segments, how many segments have we completed to complete the entire project? And we're about 50% complete because we only had 2 segments on this simplistic example. So for the second segment, I'm also going to do, I'm going to use 4 layers. And so the first is the AC, which was also 10. Layer 2 was what's that granular base, which was 9. Layer 3 did not have or was not found an embankment layer. So that was now just a coarse-grained subgrade, about 24. And under that was the fine-grained subgrade. And I'm basically going to leave everything else as defined by the program or as default for these standard typical materials, just to demonstrate what will happen. So then we're done with that. I'm going to say apply. So now everything is green. We're 100% complete. And so I'm going to save and proceed now to go to the back calculation. So we're now going to we're in part 2, and we're going to back calculate. So these are the sensors I'm going to select. I don't want to select the sensor that was used for the low transfer efficiencies. So I'm going to remove the -12 sensor, but I'm going to leave the other sensors, and I'm going to hit back calculate. So we just hit the back calculate tool, and now the program is back calculating. it was done, has been successfully completed. So I'm going to hit OK. And now it shows all the drop heights that were used, all the data was used. I'm now going to go to the different segments, and we'll look at review the results. So look at segment 1. This shows the deflection basins, and now this shows the root mean squared error for segment 1. We have up here a chart. We could either look at it in arithmetic, or we can look at it in logarithmic basis. We can also look at these values, individual layers, just the subgrade, maybe the top and bottom of the subgrade, and we can look at those arithmetically and or logarithmic. I'm going to go back though now, and I could look at just the AC, how that varies, but I'm going to include them all, and I'm going to include it in the logarithmic as we go forward. The other thing for segment 1, we're going to go look at the compensating error effects. And now we can see that for the granular base versus the coarse grain subgrade, we can see that we have a negative slope and we have an R-squared of 0.42. So that shows trends. We can look at segment 2, the lower layer. This is the subgrade embankment coarse grain versus the subgrade coarse grain. And you can see there that basically they're independent. But the key thing to point here, remember I said earlier during the presentation, are we hitting our boundary limits? And this says, yes, for the coarse grain soil above and this is the embankment, we're hitting our limit that we put into the program. The other we can see, we're also hitting the limit on our coarse grain soil also in terms of the other layer of the coarse grain soil. So we're definitely hitting the limits of some of our layers for our structure simulation. And so, but I'm going to go ahead and close this. And so now let's go to our second segment, and we'll look at our second segment. And we can see here that, we can see how the elastic moduli are varying down the road for segment 2. I can look at only a couple of the, turn that one off, and look at how my unbound layers are varying both in the logarithmic or arithmetic scale. I'm going to turn this back on to see how, and then we're going to look at the compensating error effects. So I'm going to show, and you can see that we're still, for the compensating layer effects, and again, we're still hitting the limits, but we do have some compensating layer effects here. So I'm going to close this screen down. And the other thing I want to point out here is remember our criteria for the root mean squared error. I can come in and I can say my limit, I don't want to have no more than 3, and I can do an update. And if I left it at that, this is all the data I would have for the back calculation. And so I'm going to leave it right now at not really having a tolerance, and we can see that we have quite a few values on the lower end that are much greater than 5%. A lot of values are greater than 3%. Remember, 3% would be, less than 3% is very good. Greater than 5% we probably don't want to use. So that means I need to change my structure simulation. So what I'm going to do is, demonstrate what the department finally ended up doing and give the reason for that in terms of the demo. And again, this is also to acknowledge the importance of cores in defining what's physically there and using the information from the cores for setting up the structure simulation. So I'm going to go back to my final segmentation, and there was really, the cores did not vary that much in terms of layer thicknesses. So I'm going to reset everything, and I'm only going to use one segment from the beginning to the end. And I'm going to do save and proceed. And so this one segment I'm going to apply to everything. This segment had also, from the beginning to the end, had 4 layers. The surface layer was an AC, and the department decided from cores to subdivide the AC into 2 layers, 5 inches and 5 inches. The reason for doing that, layer 1, now defined as layer 1, is about 5 inches, was a hot-in-place recycled material that exhibited signs of stripping. And so the lower layer, the bottom, about the bottom half, showed no signs of stripping. So from the cores, there was a visual observation that difference in the AC between the surface or the upper portion of the core versus the lower portion of the core. The other item is that the 9 inches aggregate base really wasn't what we would call a good quality. It may have been infiltrated with some fines over the years, and so this was defined as a granular kind of subbase or like a coarse-grained subgrade material. And so from the 9-inch aggregate gravel base with the embankment that was there was now 27. So we've combined those 2 layers, and then we left the fine grain subgrade to the end. And the other thing I'm going to change, since we hit the limits, I'm going to change the minimum values for all of these, and I'm going to, the minimum is now going to be 80,000 PSI or 80 KSI, and I'm going to set these to very low values. I'm going to change the seed modulus to more characteristic of what the core showed. And the seed modulus here, I'm going to put this up to about 30, which was used in 25. Okay? And so I'm going to now apply, and again, the reason I'm opening the minimum, I'm expanding my range of modulus values so I don't hit a limit. It's very, very low, but it wouldn't be low if we had significant stripping going on. So it's not outside the realm of a value. So I'm going to apply that and then proceed. I'm now going to again demonstrate that the sensor selection, do the back calculation, and those were run successfully. So I'm going to now look at my segment, one segment, going to see how now we can see that just turning off the, whoops, I hit it. There we go. There we go. And now you can see that the lower subgrade that we're using are now a little bit less variable, but you can see there's kind of consistent going from one end to the other where we had low deflections, now to the other where we had much higher deflections, which would indicate higher moduli on one end, lower modular on the other. So I'm going to leave both of these checked on now. And I want to look, first of all, now at compensating layer effects. And you can see now we've got really a overall positive slope, but there's not very a good relationship between the two. So we really don't have between the two unbound layers, there's really no compensating layer effects or no insensitive layer from what we've used in our layer structure simulation. So that's a good thing. So now close that. Now the other item we want to look at is our root mean squared error. And you can see when we are previous on the lower end, this end of the pavement structure, we had root mean squared errors approaching almost 10% or over 10%. Now we have only 1 point that's basically greater than 2%. So that's good. It means we've got a very good fit to our deflection basin, our measured deflection basin. The other item I should have showed and forgot about that, when we look at our unbound layers, we haven't hit a limit. We really haven't hit any limit. So we're all within the range that we have established from our layer structure simulation. So with that then, I'm going to just hit save and proceed. The other thing we're in now are physical features. So I want to define now for the load transfer efficiency for flexible pavements, our sensor numerator, that would be the -12, and under the loading plate, D0. And you can see I have all of these shown. I can click these off, and you can see that the load transfer efficiency up in our plot, they're all fairly similar. The reason I'm doing this, in some cases, in some projects, you'll see a big difference between drop height 1 versus the heavy load, drop height 4. Typically what I will do is I'll go to the higher drop height if I start seeing differences. So I can pick the one that's more appropriate. And so I'm going to leave all of these on because I'm going to use them all. And they're all very similar, so that's really a good thing also. The other the void interpretation, typically that's used for rigid pavements. We've also used this or included it for flexible pavements. The one interesting item, you can see that below about a 2, that's been established. If you got greater than 2, you have what's been defined as some kind of loss of support. Typically for rigid pavements, and it's less than 2 means you typically have a good support or no loss of support. The other thing that this load deflection basis for void interpretation, even for flexible pavement, gives you an indication that something's going on with the pavement structure from the flexible pavement that's not really typical. And if you remember from what I indicated that was shown by the cores, the first half of the project, it was really pretty good. The second half of the project was where we started seeing these stripping or the hot-in-place recycled material was used, and from one end to the other, the stripping got more and more. And you can see the void interpretation, the more and the more stripping observed by the cores, or the more loss or surface disintegration, you can see that the intercept started increasing, and then it finally exceeded 2. So this is something that the theoretical void interpretation coincided with what the core showed and led the department to realize they better do something with the top inches or top asphalt concrete, different from the lower part of the asphalt concrete. So that's just an explanation. I'm going to do proceed. And now go to our export, to part 3, to the export. And you can see with this one, I'm exporting this now to a ME design. What I want to do now, I want to tie what we used in the back calculation. I'm going to tie this to the physical default values that are in the pavement ME. So I'm going to granular subbase. I'm going to tie this to A1B, and then the fine grain subgrade, I'm going to tie this to an A27. So these now are tied to the pavement ME default values. The average modulus, you can see for the area that had stripping was about 360 KSI, compared to almost 900 KSI that did not exhibit stripping, the lower layer. The granular subbase, 25 KSI, the fine grain subgrade, about 32 KSI. This shows the standard deviation. The coefficients of variations are reasonable. You can see the coefficient of variations for the AC are relatively high, but if we see something where stripping or material disintegration going on from one point to the other, we know they're going to be high. So that's just the name of the game. And then our Poisson's ratio. So what I'm going to do now is I'm going to select an analysis type, and just to demonstrate, I'm going to say AC over AC with an interlayer. And now that's the type of rehabilitation strategy I'm going to use. And then all these others are my average. I have an average lower transfer efficiency, 68%, that will go forward with pavement ME, average pavement temperature about 80, and a load frequency of about 30 from the FWD. Export that to the pavement ME. It says it was exported successfully. So I want to take now, it says where that file was exported to, and what I want to do is that's in the Backcalculation test files. So now what I want to do is I want to go find that file. So I'm going to go where that file was created, my test files, click on that. And then I want to go to that deflection file that was set up, go to the ME design project files under that folder, and here's where the file was set up. Open that for this rehabilitation. And we now see the file that was set up, okay? So first thing I want to show is I want to go to the AC layer properties. Well, first thing I want to show is if we go to the pavement type and the design type, it is an overlay. And remember, I selected AC with an interlayer. So that is, I want to look now at AC properties, rehabilitation 1. And that's what, because it's deflection based. And you can see now we have rehab 1, and now we'd have to go through and put in all these other parameters from the site. The rut depths, the transverse cracking, we're going to mill, whatever we're going to do. So those still have to be entered. The other item I want to show, if we go to our original surface, I'm going to go to, this is the existing surface, dynamic modulus, look at layer 3. We would have to revise the percent passing here, but you can see we got 365 KSI, 365,000. There's a 30 hertz. There's about 80 degrees Fahrenheit at the pavement temperature for that layer. And so those files are, you know, the information is set up directly from the back calculation. If I go to the lower layer in place that's there, go to the dynamic modulus, then you can see the thickness, 5 inches, which we use, dynamic modulus. Going to open that. There's our almost 900,000 PSI, 30 hertz, and about 80 degrees pavement temperature. So those are all imported. So this basically set up the file correctly. I'm going to look now at the non-stabilized base or our upper embankment. There's about the 25,000 PSI that was back calculated. So since this is a back calculated value, we're in input level 1 rehab. So I have to then enter whatever correction, NDT correction value or the C factor I have to enter. Those still have to be changed, but the modulus value was imported. If I do the same thing for the subgrade layer, about 32,000, and again, I'd have to whatever C factor I'm using to convert the deflection data, input level 1, back calculated value to a laboratory value, I still have to enter those. as well as enter other values that I would normally to, traffic, climate, that are specific to my project site. But this just shows that from that segment, and we could do, if we had 10 segments, all 10 segments would be set up, and we would have a pavement ME design file for rehabilitation file already set up for our segments, however many we want to run. And so I'm going to close S and then exit out and go back to our presentation. And then in terms of the demonstration, that really concludes that demonstration, and I'll move over to our poll questions, or have Chad bring up the poll questions, and then we'll, after we get through the poll, we'll then move on to the question and answer period. So this will be the last, yes, this will be the last two questions.
1 minute.
1 minute. So if you would answer or complete the poll for these past two, or it's really three questions, so there's three questions there. If you would answer each one. Okay. Answer all three, and we have about a minute, and then we'll close the poll after that and then move forward. We have about 20 seconds left or so for the poll to remain open. Getting close to closing. Okay, about 20 seconds left before the poll closes. Waiting for everyone to submit the responses. You still have time to submit. About 5 seconds to submit the responses. And then the poll will close. Okay, we'll go ahead and save those results. I hit apply.
Hang on 1 second.
Okay.
Okay, go ahead.
Okay, so I'm going to apply them. Now I'm going to close the poll, right? Okay. So what we'd like to do now is move on to the question and answer period. And so I'm going to go through the questions.
Yeah, you should just go down the chat room.
To the chat room.
Sure, I can bring it up.
Okay.
We can just start at the bottom and work our way up.
Okay. So the first question, can they see the?
If it says to everyone, they can see it.
Okay. So this will be the last question that was and in our answers to these questions, if any others come up, or if we did not answer what, in your opinion, we did not answer your question correctly or sufficiently, please re-ask it, and we'll try to then answer it again or do a better job in that. So first is, what was the methodology to determine bound versus unbound on material behavior? Originally, that was in accordance with what you would typically see as defined by pavement ME in the manual of practice. If you have an asphalt concrete versus, Portland cement concrete, those are all considered bound. If you have a clay, silty sand, those all unbound. Where it becomes questionable is where you might have a low cement cement, stabilized soil cement, on whether it should be a stabilized or unstabilized or an unbound layer. And that is basically user defined and user classified. There are rules, I shouldn't say rules, there's guidelines in the MEPDG Manual of Practice that defines on whether we should consider a layer as an unbound or a bound material. It also gives direction on whether that unbound, let's say for a soil cement or a base stabilized material with using either an emulsion or a Portland cement on the amount of binder or additive that was used, on whether it would be a very high quote simulated as a high quality aggregate base or some other type of material. So the guidelines are included in the MEPDG Manual of Practice, and or the user obviously has some discretion. What I typically use in terms of establishing whether that's an abound or an unbound material is if I see the back calculated values like the test section, LTPP test section in Arizona, which was used a base material from the Salt River aggregate source. It has fines in it, and if those fines become very dry, they act like a cementitious type of material. And so for those types of structures, which there's a whole host of different segments that we can come up with, or type of materials, what I will do is I will simulate that as an unbound layer, but through the Pavement ME design software, but I'll simulate it as a fixed modulus, high modulus like 80,000 PSI, and I'll fix it to account for and or fix it that is dependent upon the season, whether it's in the summer to, let's say, the winter, where the moisture might be where the moisture might increase, and it may be no longer simulated as a bound or a material with a constant elastic modulus. So it's basically again, to answer the question, we go back to the guidelines on the MEPDG Manual of Practice.
Yes, that's emulsion stabilized reclaim.
Yeah, sometimes the reclaimed material, which does that pertain to emulsion stabilized reclaimed material? The answer would be yes, it would. And that layer can be, again, it depends upon how much emulsion was used, and in terms of whether it's going to react or respond as a bituminous material, asphalt concrete layer, or more like an unbound layer. And, that's going to depend on the amount of emulsion. If no emulsion, if it's like a cold-in-place material or a full-depth reclaimed layer where we're not adding any emulsion, those layers can be fairly strong or stiff, being defined as a very high elastic modulus, maybe 100 KSI, 100,000 PSI, and it depends on whether the user believes those are going to be temperature dependent or not. In previous projects, what we have assumed is when we have a reclaimed material with very low amounts of emulsion or no emulsion, we'll simulate those as a aggregate-based unbound layer with a constant elastic modulus that would simulate or be similar to the average back-calculated elastic modulus.
Okay, why don't we skip to the top there, Harold, and we'll work our way down.
Okay, we're going to go to now the top.
Because we got more people asking questions.
Okay.
Okay, so starting with Amanda, will the webinar be available on YouTube or to download? Where can we go back and watch it again? The answer is it will be available on the ME Design website at www.me-design.com, and it'll be available shortly after the webinar ends. The next one.
Okay, so yes, it will be available. Next question is from Michigan DOT, I believe Adnan and Mike. Said, is there a limit to the number of drops at a single test location? And the answer to that is no. You can have almost, a many number of drops at the same test location. The key thing is make sure that you would enter the target load for each series of test drops within that test load, and or even if they're at the same target load and or the same drop height. Next question will be also from Michigan with Mike and Adnan. Does the user have a manual segmentation, or can they just use what's been automated? You can certainly use what's been automated. You do not have to do the manual segmentation itself, but you have to identify where those segments are located. So from the automated statistical segmentation, the user would have to go in and with the cursor identify the limits. And then those limits would appear on the table on the right-hand side of the screen, and the user would simply just use those. So yes, you can use, but you still have to manually identify them.
I'll just want to jump in here. We've got a couple questions about licensing for the back calculation tool. The question is the back calculation software offered as a part of Pavement ME, or does it have to be purchased separately and have separate licenses? The answer is the license for the back calculation tool is available as a part of your Pavement ME Design license. You have a number of workstation installs available up to the number of licenses that you have available. So if you have 2 workstation licenses for ME Design, you'd have 2 back calculation licenses. If you had a 9-user site license, you'd have up to 9 workstation installs for the back calculation tool currently.
Okay. Thank you, Chad. Next question, also from Michigan, Mike and Adnan. Does the tool automatically flag unacceptable or atypical root mean squared errors? The answer to that would be no, it does not automatically tag them. It lists all of those in the chart where it plots the root mean squared error for each test drop as a function of distance, and the user would then need to go in and identify the limit as 3 or criteria as 3%, 5%, or whatever the limit the user wanted to use. And the program will only use those deflection basins with the root mean squared error equal to or less than the RMSE criteria the user entered. Again, we're suggesting that for very large projects that you, as a user, not use any value where the root mean squared errors are greater than 5%. Okay, next question is going to be from Chetna Rao. And Chetna asks, can the user redefine the criteria for acceptable, atypical, or unacceptable results? The answer to that is yes. The user for the root mean squared error, you can enter as the one for Michigan, you can enter different values, root mean squared error values, and the program, as long as you hit update, will use that updated or specific value the user enters. Second part of the question is, also, can the user define the modulus range for typical and atypical results? The program simply, as a root mean squared error, would plot the results out on the longitudinal plot of that elastic modulus values versus distance. The user would have to look at those values and define whether they're too high or too low. The program does not, as long as the root mean squared error is less than the criteria, the program is going to use all of the elastic modulus values. So if, for example, we have test points that have root mean squared errors less than 5% of a root, and that would be the criteria, and we have a modulus value that the user does not want to use in terms of determining the average value, they would have to physically eliminate the deflection data for that one test drop and or test point. So the program would not do that automatically.
One from Clark Graves, I'm going to read it here.
Okay, Chad is going to read one from Clark Graves. Go ahead.
In the segmentation portion, wanted to know if they're raw deflections or if they've been adjusted for temperature.
That's a very good question, and that was an item that was debated in setting up the Backcalculation tool. And we relied on the results and the recommendations from the Federal Highway Administration, LTPP Backcalculation studies and guidelines. And even if you look in the MEPDG Manual of Practice, it also makes comments on what you should do about the temperatures as well as converging to a specific drop load or adjusting to a drop load. It does not adjust temperatures to or deflections to a standard temperatures. It uses whatever those raw deflections are at the temperatures that were entered, either at the air or temperature and or air temperature and pavement temperature. So it uses the actual temperatures recorded during the deflection. Any adjustment to temperature down the road would be made by the pavement ME and or the user itself for adjusting the different temperatures from a modulus standpoint, like using the master curve. It also does not adjust to a standard load. It uses the average standard or the load drop measured by the FWD to whatever those deflections were measured by the geophones on the FWD.
Got a few more.
Go ahead, Chad.
So we have a question from Les. Can users use this tool to compute subgrade K value for rigid pavement and input for rigid pavement rehab design?
At the present, no.
Okay. Next question, again from Clark. Is there an option to export the individual layer moduli by station? Generally, we like to plot this up as a part of our evaluation process for potential rehab. An option to export the individual layer moduli by station.
If you define the station as a segment, then the answer to that question is yes. If not, then the answer would be no.
Okay. That's all the private ones I have up to the next everyone.
Okay, I'm going to go back. Okay, one question is to make what method is used for temperature correction of the raw deflection data. That was asked by Orma, and there are no corrections to temperature for the raw deflection data. The only temperature corrections would be made would be to the from the master curve after the elastic modulus are determined. What was it?
You got another.
The other, let me ask that this one is from Dr. Hayter. It says, how is a standard deviation or coefficient of variation used in the pavement ME design? The coefficient of variation and standard deviation are not inputs to the pavement ME design itself. The standard deviation and coefficient of variations are only used by the user from the back calculation tool to make a judgment on how variable the modulus of that layer is. For example, in our demo, that coefficient of variation and standard deviation for the asphalt concrete layers were very high because there was stripping going on, whereas they were what I would consider reasonable for the unbound layers on what you would typically see in terms of variation of other material properties along a project length for unbound layers, soils, aggregate base materials, somewhere around 20%, 25% coefficient of variation. So those values are only used as a guide for judging the back calculated values for each of the different layers before we establish a .dgpx file for a pavement ME design run. Another question by Dr. Hayter is, how is the speed of back calculation? And I'm not sure I understand what speed in terms of back calculation means. If it means in terms how long it takes to do the back calculation, it's very quick, very, very fast, because EverCalc is a very, very fast operational tool. If the question is more related in terms of speed related to hertz of the FWD, that is, it's only considered in terms of the damage, establishing the damaged modulus curve for flexible pavements for the rehabilitation design. And the default value, as recommended from the long-term pavement performance study for back calculation, was 30 hertz, which is also recommended by other studies, not only the long-term pavement performance. So 30 hertz in terms of an input to the pavement ME design is what's recommended and what's defaulted. But the user can change that. Okay. Another one, question from Peter, is the version of EverCalc used different from version 5.0? That EverCalc version 5.0 is the version in the pavement ME design, because that is the version, as I recall, that was provided to AASHTOWare by Jeff and Washington DOT. So I think that is the 2005 version. So the latest version of EverCalc is included in the AASHTOWare pavement ME back calculation tool.
It's been updated to run on Windows 8 and Windows 10. Yeah. There's one question about licensing from ARMA. Did you see that?
Would you go ahead?
Yeah. Well,
go ahead.
I can give my best answer.
Yeah, Chad will give the other question that ARMA asked.
So the licensing for EverCalc, the question is, how does licensing for EverCalc work? Will it be linked with the pavement ME license? We don't provide a separate license for EverCalc. As I understand it, the folks from Washington provided us with the EverCalc source code, knowing that we'd be integrating that with this tool. So we don't have any sort of licensing association with the EverCalc software.
Another question, also Michigan, Mike and Adnan, is there a key for the colors? And I'm assuming the colors here are the colors for when the segments are completed in terms of establishing the segments as we go from no colors to a green. And there's really no key for a color other than green's ready to go. Yellow is, or light orange is, we're in the process of working within that segment. And no colors means we haven't, or you haven't looked at that segment yet. If the colors are related to, let's say, the plots of modulus versus distance and the logarithmic and or arithmetic graphics of the modulus versus density, those were simply default colors that were selected. There's no significance to those colors.
There was one screen that didn't have a legend on it. I think it was in selecting the drops that he's referring to, which if there are any graphs that currently don't have a legend, we'll make sure we get a legend on there.
Chad said that there may be a few graphs in terms of selecting the sensors.
I think it was the sensor selection.
Sensor selection that had a color, and we'll go back through, and if there are any colors related to sensor selection or so that we'll definitely make, and they have some significance, we'll add a legend to those color designations. Okay. Another question, which is is a good question. This is Aid. Can this application load thicknesses from GPR? At present, and no, it does not. So, and in addition, thicknesses from the cores do not automatically get added. But the user certainly can use thicknesses from GPR in the back calculation process. If the thicknesses are highly variable, let's say from the GPR, ground penetrating radar study or field measurements, that simply, and a user wanting to consider all those thickness differences, what that implies is you would need to have many more segments, because a segment as defined in EverCalc means we have the same layer structure meaning layer type as well as layer thickness within that segment. So the results from GPR certainly can be used, but if the actual thickness are being used, then that means you would need almost like a test point segmentation basis.
We've got about 3 minutes before we're supposed to be done. I wanted to address an important question regarding saving.
Okay.
So Clark asked, are these results saved so they can be reviewed again, or do you go through the back calculation process again? I know we have a saving feature, so maybe you could.
Yeah, you can save. Repeat that question one more time.
So Clark's asking, are the results saved so they can be reviewed again, or do you go through the back calculation process again, including like having to create your segments and that kind of stuff?
The back calculation project is saved up to the point before the back calculation is invoked through EverCalc. So every step from loading the FWD data up to selecting the segments and inputting the structure definition for each segment, all of these progress will be saved when the user proceeds to the next step. So the user wouldn't need to input all of the structure definition again for each segment before the back calculation step.
And how does it name the save file?
In the first screen, when the user chooses the FWD data, there's another file type called .bct project. That's the file specifically for the back calculation project. It's the saved project for any previous progress related to the same name of that FWD file.
Great.
Okay, another question from Dave Miller. How do you select just one or two sensors for the segmentation? Again, what I would do is the program doesn't allow you to do over 3. If you wanted to use one, I would use D0, but it's basically up to that's at the user's discretion. I always use D0, and at the other one I always use is the one furthest from the load, D60 or whatever the greatest distance is. But that's totally up to at the user's discretion. Another one for Peter had. EverCalc allows layer thicknesses to be varied on a basin-by-basin basis. Can this tool do that, or the layer thicknesses only by section average? The user can do that, but that would be on a segment basis, so you would have to enter for each test point or each station a different thickness and create that a segment for that station. Okay, how much time do we have?
Technically at 3 o'clock now.
Okay. I'll answer this one. This is also for ARMA. Is a field to lab adjustment factor applied? It is applied in the pavement ME, and that is default to 1, as it is for all pavement ME design, and the user has to physically go in and revise that to whatever C factor applies to that layer and material type. So the user has to physically revise it or alter it. Okay, with that, I think we're going to close the question and answer. And
just want to say,
go ahead.
Yeah, we'll be taking down all the questions that have been asked in the webinar. If we didn't get to your question during the webinar, we'll get that answered, and that'll be posted to the ME Design website and available for you all to look at and comment on.
So is John still? John, I'll let you then.
Let me unmute him here.
Okay. Just before I turn it over to John, I want to thank everyone from our end for participating. As Chad said, we'll go through all the questions and we'll make sure they're all answered, and that will be sent out to all participants that signed in. So with that, John, I'll turn it back over to you for any closing comments.
Well, first, I'd just like to thank you, Harold, and Chad, and Yanbin, and all the others at ARA that have been involved in developing the Backcalculation tool. And as you can see on the screen there, I want to put in a plug for the second Pavement ME Design User Group meeting, which is going to occur in October 11th and 12th in Denver. And we certainly invite anyone to come that's interested in being there. There should be a lot of good information presented there. There was at the last meeting in Indianapolis last December. And with that, I just want to thank everybody for listening. And again, we appreciate and desire your input. Anything we do on the task force, we do with the intent that we're trying to represent what the users want, and trying to in a fairly democratic fashion, institute changes and improvements to the software to make it more desirable with every version that is put out. And so with that, I just thank you and say goodbye.
Great.
Thank you all. And I will unshare.
Yeah.
Oh, stop share.